good evening. My name is Valeria Armendariz, and I'll be presenting my project on the mass spectrometer. This project was made by myself and Agustin Jimenez for Physics 2401 with Dr. Farouk for HE+. So please enjoy our presentation on the mass spectrometer. Introducing the mass spectrometer, this is an analytical technique used to separate ionized particles to predict their mass-to-charge ratio. The data is then presented in a chart that can be analyzed by different communities used for pharmaceutical analysis, forensic analysis, and environmental analysis, as used in communities for us as physicists, biologists, or even chemists, or any other fields. How this functions is that there's three main components: the ion source, a mass analyzer, and a detector. The ion source is mainly used to ionize the sample, a mass analyzer is what makes the mass-to-charge ratio that we know, and the detector is what records this and sends it out as per the results. Some history is that it dated all the way back to 1897, but it's now used till this day and has evolved a lot. Starting with some history, the main founder of this, J.J. Thomson, who is also very much known for the founder of the electron, built the first mass spectrometer in 1912. This was originally known as the parabola spectrograph, but it was used for uncovering the existence of non-radioactive isotopes. This was first built with him and his lab assistant E. Everett, which measured EM, which is now modernly known as MC, which is the charge-to-mass ratio. The first machine was used to find magnetic deflection of cathode rays, as quoted by Griffiths. This laid out the foundation of the MS field, and Francis Ashton, who was a protege of Thomson, built the next first mass spectrometer that actually measured the mass of charged atoms as a whole. Continuing this, the mass spectrometer has evolved a lot from its time from when J.J. Thomson first worked on it. Up until the 1940s, physicists mainly dominated the field, but because of a man named Alfred Neer, who was an electrical engineer who did his graduate work in physics, he served well on his journey on making this mass spectrometer more well known to communities outside of physicists. This was done by the commercialization of it and just promoting it to different types of communities. As quoted by Schluter in 2008, he sort of commercialized the instrument not in the sense that he was trying to sell them, but to make them more useful. And this was very much helpful as we use them very much today in many different fields for many different things. Now, going into how it functions, there are four main stages in the mass spectrometer. There is ionization, acceleration, deflection, and detection. The sample for the mass spectrometer needs to be ionized. This can be done through the gas chromatography, liquid chromatography, which are most common ways of samples being done for the mass spectrometer, but some other ones that are mainly well used and well known are also the electrospray and proton transfer reaction mass spectrometry. There's also a lot more that will be mentioned later on in this presentation. The sample is then usually put into the mass spectrometer through a syringe that will then be vaporized and then led to the next step. The next step being that of ionization. This is where it's vaporized and passed into an ionization chamber. Inside this chamber, there is a plate that attracts electrons and then a heated metal coil that is giving off these electrons. Because of these electrons, positive ions can be formed because of the sample ions and then these electrons bumping into each other, picking up positive charges, which then gives these positive charges into what will be known as we used in the mass spectrometer. An ion repeller then leads these ions out, so it's able to go into the next few steps. Its acceleration being the next step, which it has is three slits. It has the first one, the intermediate plate, and then the final plate, which is at 0 volts. In this plate, we have an ion beam, which is all the focused positive ions being focused into the next parts. All of this is happening when they have equal kinetic energy as they're working with the magnetic field and the current of it all. The ions are then repelled into the positive ionization chamber, which will lead to the next step. The next step being deflection. Ions will deflect by different amounts of different magnetic fields. So usually this is happening because of the different positive charges. The usual positive charge is a +1 charge in this field, but there are sometimes more and sometimes there's a little bit less or none. So then this is where we get different streams. Streams A, stream B, and stream C. Stream A is usually known as the most deflected, having the smallest MC ratio. Then we have stream B and stream C having our biggest. So this usually has our most positively charged ratios and ions. This is where also the MZ is formulated, so we'll be able to go into the next part of our mass spectrometer, which is the detection. In the detection, stream B is made into an ion detector if we're doing by ideal circumstances. The rest of the ions that are in stream A or stream C usually are collected at the walls. In the walls, the Faraday cup is what collecting them and neutralizing them by giving off electrons from the metal of the sides to make these a zero charge or a neutralized atom. So when it collects them, and then the vacuum pump can come in and clean them out. Now it's very important that the mass spectrometer is in the vacuum, so these ions are not traveling elsewhere that they don't need to be, so that we're able to get our best results for the mass MZ. Then ion detector then lets these ions enter from our stream B. And then because it's into a metal box, our metal box then neutralizes these atoms. And then with these atoms itself, there's a little small wire. Since electrons are being moved up and picked up, it's going to pick up these electrons and then keep spreading them out so that more ions come in, more ions are able to pick up these negative charges from these electrons. Other streams can be mated into this electron box if we can use to manipulate the magnetic field and current that's being used. When we get our output and our results, we usually get a simple stick diagram that is sent to the computer so that scientists don't have to go in and manually get this stuff. Usually this is showed in an X and Y axis, Y axis being relative abundance or relative intensity, and then the X axis being MZ. This is proportional to the current received from the chart recorder, so essentially the greater the current, the ion is more abundant. Some applications of this happening can be seen in pharmaceutical analysis, such as the drug discovery. In outset, we have a hit identification phase. This phase is where the mass spectrometry pinpoints compounds with potential therapeutic effects. So this is where we find what we want ions to do in certain medications that we have. So in the hit to lead optimization, subtle modifications are made to the chemical structure. So this is where we're able to manipulate some structures into what we want for medication. Our validation for the hit completes a detailed characterization and identification of its target. So this is how we want with it interacting with our body to get our best results. Some other forensic analysis, we have toxicology, arson and explosives, and trace evidence. In toxicology, we have LCMS, which is the liquid chromatography mass spectrometry, which a substance itself, like human tissue, can be used to find some things. This can be used to confirm whether an individual ingested a harmful substance or if something was put into their system. In our arson and explosives, we have GCMS, which is gas chromatography mass spectrometry, which is to high volatile samples. This can test if some samples and determine if there's been a flammable substance or if there's something happened to the body or around someone that's able to happen. And in trace evidence, we use IRMS, which is isotope ratio mass spectrometry, and we use identical samples, but we can find differences in them, whether knowing if they're from the same tissue or from different tissues or same bodies or different bodies. In environmental analysis, we can use this for water analysis, again with arson and explosives and trace evidence. In water analysis, we use again the liquid chromatography mass spectrometry, which we can find potential contaminants even at very low levels. And again, with arson and explosives, we can use proton transfer reaction mass spectrometry. And this we can be able to use to find air quality. So we're able to find pollutants or any sort of pollution going on in the environment, even at low levels that we wouldn't be able to detect with the naked eye. And again, with trace evidence, with LCMS or liquid chromatography mass spectrometry, we can use this to find contaminants in our soil. So we're able to tell if there is something going on with the soil or if we should be worrying on something even at very low levels, so we can take action very early on. This can include just like industrial waste, pesticides, POPs, or PPCPs. So we have some worked out problems for you for the mass spectrometry to better understand how this works. This can be done in a more chemical type of way, but we're going to do it in a more physical type of way for the sake of this project. So for our first application, we have the circular motion of moving ions in a uniform magnetic field. Find the mass of an ion moving of the detector. Here we have our picture of the ions in these dotted lines moving into the detector from the ion source. We have it going through the magnetic field, going in a circle, and we need to find the mass of it. So with it, ideally, we would have our radius. So our radius would be mass times velocity over charge over magnetic field. So when our charge can be later be found as electric charge or electron charge. So our kinetic energy, as mentioned before, has to be equal to, in all cases, to get into the ion detector. So kinetic energy will have to equal potential energy. So in this case, we will have 1/2 mass times velocity squared equal to EV. So we're trying to find velocity here to be able to find our mass. So velocity will have to equal EB times R over M. But since velocity is in the kinetic energy formula, we will have to square everything in that. So now our new kinetic energy formula will be E squared R squared over 2M times B squared, which is still equal to the potential energy of EV. Now rearranging all that to get M by itself, we have the new equation of ER squared over 2V times B squared. Another problem that we have here is a slightly charged positive ion has a mass of 2.5 times 10 to the negative 26 kilograms. After being accelerated through a potential difference of 250 volts, the ion enters a magnetic field of 0.5 Teslas in a direction perpendicular to the field. Calculate the radius of the path of the ion of the field. Here we're given charge, mass, potential difference, and our magnetic field, and we need to find radius. So we know that we have a perpendicular direction to the field, so that's where we have F of B and F of C. F of B being the magnetic field and F of C being our centripetal force. So because of this, we know that our maximum magnitude will be sine of theta equals 1. So with that, our sine of F of B will be QVB. And then our centripetal force will be equal to MB squared over R. So rearranging all this together, we can get the radius is equal to MB over QB. But since we needed to find V, to be able to find R, we will have to rearrange another equation to be able to find what V equals to, using our known equations. So we have our potential difference, which would be equal to W over Q, or the same thing as the change in kinetic energy over charge, which would just be 1/2 MV squared over Q. So rearranging all this, we can get V to the square root of 2 delta VQ over M, and then putting in our knowns that we have already, we have 5.66 times 10 to the 4 mass per second, meters per second as our velocity. So using that and then putting it back into our radius equation, we can find that our radius of this path will be 0.0177 meters. For our next problem, we have what is the velocity of the nickel atom as it exits the electric field shown above, and we're assuming the initial velocity is about 0. So here we have our picture of our nickel atom leaving the mass spectrometer, and we need to find its velocity. So we have our given of the mass, our potential difference, and our electric charge. And so using the solution, we can find that K initial plus U initial equals K final minus U final. Now knowing that our initial K is 0, we can just input 0 in and then rearrange it so we have our U's on one side and our K's on one side. So that's where we get U initial minus U final equals 1/2 meter mass times velocity squared, which is our kinetic energy equation. Now knowing this, we have U equals QV. So inputting all that into the new equation, we have EVI, since Q is our charge, but we will be using E as our electron charge. So then we have EV initial minus EV final is equal to 1/2 meters times mass times velocity squared. Now, since E is our constant here, we can take that out and factor it, and now we have E times V initial minus V final is equal to 1/2 meter mass times velocity squared, in which we can input all our knowns in together, and we can get V by itself to get to the square root of 2E times 3000 over M.